Well, if we feel bored, what we do? We use Twitter, YouTube, or some other application. Every day, millions of users are using these applications, and a massive amount of data is getting generated. But we never think how these applications are maintaining such a huge volume of data. It's interesting, right? So let's explore this exciting content together. Interacting with databases became a regular part of our life, but most of us couldn't be aware that we are dealing with a database. We can see database applications in almost every industry. In banking, we use database applications for customer information, loans, banking transactions, etc. In airlines, for reservations, schedule information, and so on. In telecommunications, for keeping calls data, maintaining balance information, etc. And there are many other fields like finance, sales, manufacturing, where we use these database systems. Traditional database systems are used to store traditional data such as textual or numeric data. For example, storing student data in a school application. Multimedia database systems are used to store images, audio, and video clips. Geographic information systems, GIS, are used to store complex data like maps, weather data, satellite images, etc. For example, Google Maps. Due to the advancement in technology, many exciting database systems were designed. In the recent times, social media sites like Facebook, Twitter, and YouTube has a huge requirement to store non-traditional data such as posts, tweets, images, and video clips. These kind of non-traditional data can be stored in big data systems or NoSQL systems. Let us go back to our schooling days. We all had friends in our school, right? If we had a few friends, we could remember their details. But if we had hundreds of friends, then what should we do to remember all their details? We could write the details like names, addresses, contact numbers, and so on in a file. These individual pieces of information that we collect are called data for friends. Here, we can use a file to store the data in a physical form or on a computer. If the data is growing, it will create many problems like occupying more space, physical damage, unauthorized access, difficulty in accessing or updating the data if we store thousands of files with no proper order. So, what can be a solution to this problem? We need to organize those files in some order by name or by section or by some other means so that we can handle them easily. Collecting all the related data together and arranging it by some order is nothing but creating a database. So, a database is a systematic collection of related data. Let's have a look at a sample school database. A school database can have the following files: a student file to store student data, a course file to store course data, a grade file to store grades of each student. If we want to access or modify a particular student data, we need to open that corresponding file and make changes, which takes manual and laborious effort. If we are smart enough, we can create an application to access and modify these files automatically. This is called traditional file processing, but this process is very time consuming if the file contains thousands of records. Accessing multiple files and updating these files leads to data inconsistency and data duplication. To overcome these problems, we have a software that is a database management system or DBMS. In the 1960s, the first DBMS software was introduced by Charles W. Bachman. The DBMS is used to create and maintain a database. When we create a database, its description is stored in DBMS catalog. The catalog contains metadata. Metadata is the data such as the structure of each file, type, and storage format of each data item. When a request is made to access the database, DBMS will refer to the catalog to know the structure of the files in the database. Till now, we have discussed a database and a DBMS software. Now you may ask what a database system is. A database and a DBMS software together called a database system.
History of the database systems. Early databases are file-based and data was maintained in flat files. In the early 1960s, Charles Bachman developed the first DBMS, Integrated Data Store, at Honeywell. The Integrated Data Store used a network data model. In this model, files are related as owners and members. Each member file can have more than one owner. In the 1960s, IBM developed its first DBMS software called Information Management System. IMS was a hierarchical database model. In a hierarchical model, files are related in a parent and child manner. Each child file has at most one parent file. E.F. Codd conceived the relational database model in 1970. This model uses the concept of mathematical relations, which looks like tables. In the 1980s, to store and share complex and structured objects, object-oriented database model was introduced. It supports the modeling and creation of data as objects. In the 1990s, due to the requirement of object capabilities, the relational database also incorporated object features, which led to ORDBMS. ORDBMS combined the object and relational concepts. In the 2000s, big data and NoSQL systems were developed to manage massive volume of unstructured data and to provide faster search and retrieval. Now we will learn terms in DBMS which will be useful in the next lectures. Data models, schemas, and instances are the fundamental concepts to understand the architecture of the database systems. Data model. It's a collection of concepts that are used to describe the structure of a database. Data models are used in database design to ensure the design is providing data abstraction. There are three levels of data models: high-level, representational level, and low-level data models. High-level or conceptual data model. It provides concepts for how users perceive data. High-level model uses concepts like entities, attributes, relationships, etc. For example, entity relation model. Representational or implementation data model. It is easy to understand but hides many details regarding how data is stored on the disk. Relational, network, hierarchical, and object data models are examples of this model. Low-level or physical data model. It describes how data is stored in the computer storage. These low-level data model concepts are generally used by computer specialists to design and implement efficient storage systems. And there is one more data model called self-describing data model. This model combines the description of data with data values themselves. These models include key value stores and NoSQL systems, which are used in maintaining big data.
Data abstraction is one of the main features of the database systems. If the application programs are independent of the structure of the data, it is program data independence. So even if we add a new column, we no need to change the application program. If application programs are independent of how the operations are performed on the data, it is program operation independence. So application programs need not be changed even if the DBMS software changes the implementation of the internal operations. We can say a database system is providing data abstraction only if it can support both program data independence and program operation independence. Data abstraction hides irrelevant details and provides an abstract view of the data. Data abstraction can be in three levels: physical, logical, and view level. Physical level describes how the data is stored in the storage. It is the lowest level of abstraction. Logical level describes what data to be stored in the database and what relationships exist among the data. View level describes only part of the database. The system may provide many views of the same database. Each user can see a different view of the database, and it is the highest level of abstraction. There are two types of languages in DBMS: DDL and DML. Data definition language (DDL) is to create a database and its schema. Data manipulation language or DML is to query and update the database. Practically, these two languages are part of a comprehensive language called Structured Query Language or SQL. The output of DDL is placed in the data dictionary or catalog, which contains metadata, that is, data about data. The data dictionary is a special type of table that can only be accessed and updated by the database system. A user cannot update the data dictionary. DML offers many features like retrieval of information, deletion of information, updation of information, and insertion of new information. There are two types of DMLs, procedural DMLs and declarative DMLs. In the procedural DMLs, the user needs to specify what data is required and also needs to specify how to get the data. In declarative or non-procedural DMLs, the user just needs to specify what data is required and need not specify how to get the data. DML can be used in a standalone interactive manner or through an application program. There are three key types of people involving in designing, maintaining, and using a database. Database designers are responsible for identifying the data to be stored in the database and its design. Database administrators are responsible for authorizing access to the database and administering it. Users access the database for querying, updating, and generating reports. There are many other types of database users. We will discuss that more clearly in further topics.
Database schema. It is the description of a database. It is specified during database design and it won't change frequently. Schema diagram. Schemas can be represented pictorially using data model concepts. A pictorial schema is called schema diagram. Each object in the schema diagram, such as student or course, is a schema construct. Database state. Unlike schemas, the actual data in a database may change quite frequently. Every time we add a new student, the data in the database will change. The data in the database at a particular moment is called a database state or snapshot. Every time we modify a record, we are changing one state of the database into another state. When we define a new database, we only specify its database schema. At this stage, the corresponding database state is an empty state with no data. We get the initial state of the database when it is first populated or loaded with the initial data. From then on, every time an update operation is performed, a new database state is created. At any point in time, the database has a current state. Valid state. It is a database state that satisfies the structure and constraints specified in the schema. DBMS is responsible for ensuring this valid state. Specifying a correct schema to the DBMS is extremely important, so the schema must be designed with utmost care. The schema should not change frequently, but it can be changed if the application requirements change, which is called a schema evolution. 3-schema architecture is a tool for visualizing the schema levels in a database system. It has 3 levels: internal, conceptual, and view level. Internal level has an internal schema. It gives us complete details of data storage and access paths for the database. Conceptual level has a conceptual schema. It hides the details of physical storage structures and concentrates on describing entities, data types, relationships, user operations, and constraints. External or view level includes number of external schemas or user views. Each user group can access some part of the database only, and it hides the rest of the database from that user group. These 3 schemas are descriptions of data. The actual data is stored at the physical level only. A transaction is an executing program or process that includes one or more database tasks. A task can be reading or updating records. For example, a person is withdrawing funds from his account is a transaction. This transaction has simple tasks: reading account balance, deducting the amount from his account, writing the remaining balance to his account, giving deducted amount to the person. The transaction must happen completely successful or completely failed. This all or none property is called atomicity. It is essential that the execution of a transaction must preserve the consistency of the database. That is, it should preserve the remaining balance after withdrawal. This property is called consistency. After successful execution of a transaction, the database must preserve the new account balance irrespective of the system failure, which is called the durability. And also, even there is a number of transactions executing concurrently, each transaction should execute independently. It is called isolation. These atomicity, consistency, isolation, and durability are called ACID properties. Transaction Manager. It ensures that the database remains in a consistent or correct state despite the system failures and transaction failures. Concurrency Control Software. It controls concurrently executing transactions. Data independence. It is the capacity to change the schema at one level without having to change the schema at the next or higher level. We have two types of data independence: logical data independence and physical data independence. Logical data independence. It is the capacity to change the conceptual schema without having to change external schemas or application programs. We can change the conceptual schema by adding or removing a record type or data item. It should not affect the external views or applications. Physical data independence. It is the capacity to change the internal schema without having to change the conceptual schema. Hence, the external schemas need not be changed as well. Internal schema won't change frequently. Typical reasons for internal schema change are adding new storage devices, using different data structures, changing from one access method to another, and modifying indexes. Data storage and querying. Both database and DBMS catalog are generally stored on disk. The operating system controls the access to the disk and schedules disk read and write. Many DBMS software has their own buffer management to schedule disk read and write because management of buffer storage has a considerable effect on performance. Stored data manager in the DBMS controls interaction with file manager, efficient storing, retrieving, and updating of data. DDL compiler. It processes schema definitions specified in the DDL and stores descriptions of the schemas in the DBMS catalog. Query compiler. It parses and validates for the correctness of query syntax. It compiles queries into an internal query form which will subject to query optimization. Query optimizer. It uses efficient search algorithms and consults the system catalog for statistical and other physical information about the stored data and generate executable code. This code performs the necessary operations for the query and make calls on the runtime processor. Precompiler. It extracts DML commands from the application programs. These DML commands are sent to a DML compiler for compilation into object code for database access, and the rest of the program is sent to the host language compiler. The object codes for the DML commands and the rest of the program are linked and forms a CANET transaction. CANET transactions are the standard queries that are used to query or update the database constantly and is repeatedly executed by parametric users via PCs or mobile apps. They simply supply input data to the CANET transactions. For example, in a bank payment transaction, the account number, payee name, amount may be supplied as parameters. Each execution is a separate transaction. A runtime database processor executes privileged commands, executable queries, and CANET transactions with runtime parameters. It updates system catalog with statistics of the data. It also works with the stored data manager, which use essential OS services for doing low-level I/O operations between the disk and main memory. It also handles data transfer like buffer management in the main memory. Some DBMSs have their own buffer management module, whereas other depends on the OS for buffer management. There are two types of database architectures: centralized and client-server architecture. Centralized architecture is an old style of architecture where users access database via computer terminals. These terminals have only display capability but not the processing power.
So these terminals can't run any other applications.
All the processing is performed remotely on computers running with DBMS. Only display information is sent to the terminals. Here, the central DBMS computer is a bottleneck of the system. Gradually, database systems started evolving by sharing some of the processing to the user side, which led to the client-server DBMS architecture. It was developed to deal with environments where a large number of PCs and workstations are connected via a network, and the network can be wireless, LAN, internet, etc. Client. It is a user machine that has the local processing power and also interfacing capabilities with the database server. Client applications like Java and .NET will run on these machines. Database server. It is a system that provides database access to the client machines. A DBMS software runs on the database server, for example, SQL Server, Oracle, MySQL, or some other. The client and server software typically run on separate machines, and they can sometimes be on the same machine in development environment. The advantages of this architecture are its simplicity and compatibility with existing systems. There are two types in client-server architecture, 2-tier and 3-tier. In 2-tier client-server architecture, client and server act as 2 tiers.
For most of the DBMSs, SQL is the standard language.
The query and transaction functionality related to SQL processing lives on the server side, so the server can also be called as query server or transaction server. The user interface programs and the other application programs can run on the client side. A standard called Open Database Connectivity provides an application programming interface or API between the client and the server.
If both the client and server machines have the necessary software installed, the client-side programs can establish a connection to the DBMS server.
Once the connection is created, the client program can communicate with the DBMS. A client program can connect to the several DBMS software and can send query and transaction requests using the ODBC API, which are then processed at the server sites. Query results are sent back to the client program, which can process and display the results. A related standard for the Java programming language is called JDBC or Java Database Connectivity, which allows Java client programs to access one or more DBMS through a standard interface. The emergence of the web changed the roles of clients and servers, which led to the 3-tier architecture. Web and enterprise applications use the 3-tier architecture. The intermediate layer or middle tier is called application server or the web server. The web server runs server application programs or procedures and stores business rules or constraints which are used to access data from the database server. The web server accepts requests from the client, processes and checks the client's credentials before forwarding a request to the database server, and it passes the partially processed data from the database server to the clients, where it may be processed further and filtered to be displayed to the users. Thus, the user interface, application rules, and database access act as 3 tiers. We also view 3-tier architecture as the presentation layer, the business logic layer, and the database service layer. The presentation layer displays information to the user and allows the data entry. The business logic layer handles intermediate rules and constraints. The database services layer includes all data management services. To have high maintainability and easy bug fixing, the business logic layer can be further divided into multiple layers as well. This leads to entire architecture.
Data mining is the discovery or mining of new information from the vast amount of data in terms of patterns or rules. Data mining is also known as data discovery or knowledge discovery. The data mining process includes the following stages: extraction of data from data repositories, data cleansing and loading into mining database, data transformation, pattern discovery using algorithms such as clustering, regression, classification, and finally, data visualization and interpretation of results. Data is of three types based on the format it is available: structured, semi-structured, and unstructured. Examples of structured data formats can be relational data like tables and views in Oracle MySQL. Examples of semi-structured data formats can be XML and JSON. And examples of unstructured data formats can be PDFs and MP3s. Textual data like posts, tweets, and documents is unstructured. A document can be a unit of retrieving text, a web page, an article, a book, a section, or chapter. Querying of unstructured textual data is known as information retrieval. When a user executes a query into the information retrieval system, it will search a collection of documents. The system will compare the terms in query to the terms in the documents and give ranks based on the similarity. The top-ranked documents are more relevant for the query, and it will process the relevant documents for the user. Specialty databases. It is hard to design database systems for complex application areas like engineering design, manufacturing, and geographic information systems. These database systems require complex structures for storing objects. Some of these specialty databases are object-based and semi-structured data models. Let us see what is the object data model. The object data model defines a database in terms of objects, their properties, and operations. A typical object has two components: state or value, behavior or operations. Objects with same structure and behavior belong to the same class. The operations of each class are specified in terms of predefined procedures called as methods or functions. We have seen what the object data model is. Let us discuss about the semi-structured data model. A semi-structured data model has no separation between schema and the data. In semi-structured data model, data comes with its own description. So, these data models are self-describing data models. XML and JSON are examples for this model. XML and JSON documents provide descriptive information such as attribute names as well as the values of these attributes. So in this video, we have discussed about what is data mining, the types of data formats, information retrieval, and finally the types of specialty databases.
A database application refers to a database and its associated programs. These programs will query and update the database. For example, a bank database application includes a database and programs corresponding to customer deposits and withdrawals. To create a database application, we first need to design the database. There are 5 different phases to design a database, and they are requirements collection and analysis, functional requirements analysis, conceptual design, logical design, and physical design. Let us see each phase in detail. In requirements collection and analysis phase, designers will talk to users or clients to collect the data requirements. Designers must concentrate on properties and domain information of the data to be stored. In functional requirements analysis, along with the data requirements, designers also need to analyze the functional requirements of the application. These functional requirements are user-defined operations or transactions that are performed on the data, and the operations on the data can be retrievals, insertions, modifications, deletions, etc. All these requirements must be properly documented. In conceptual schema design, designers will identify entity types, relationships, constraints, etc. by analyzing the functional and the data requirements. Conceptual schema is a brief description of the user's requirements and detailed description of entity types, relationships, constraints, and so on. It describes the semantics of a database. Conceptual schema design ensures all the data requirements are met and the requirements do not conflict. Remember these terms for now. and we will explain them later. In logical design, conceptual data model is converted into the implementation data model, where we finalize the whole database design logically by considering many aspects like security and performance, etc. It is also called as data model mapping. Please remember that it is just a pictorial design. The actual database will be implemented using DBMS software like MySQL or Oracle, etc. In physical design, the parameters like internal storage structures, file organizations, indexes, access paths, and physical design parameters for the database files are specified. Before getting into the database design process, we first need to understand basic terms and concepts in the database design. Entity relationship model is an example of the conceptual schema. It describes the database as entities, relationships, and constraints. An entity is a thing or an object in the real world with independent existence. The object needs to exist physically or conceptually. For example, an entity can be a physical object like a car or an employee, or it can be a conceptual object like a job or a university course. Each entity has some properties that describe it. These properties of the entities are called attributes. For example, an employee entity can have name, address, age, salary, and phone number attributes. There are several types in attributes, and they are simple, composite, single-valued, multi-valued, derived, null, and complex attributes. The simple attributes cannot be divided further into subparts. For example, salary attribute from the employee entity cannot be divided further. The composite attributes can be divided further into subparts, which have their own independent meaning. For example, the address attribute of the employee entity can be divided further into street, city, state, and zip code. The single-valued attributes can only have any single value but not a set of values. For example, age is a single-valued attribute because an employee cannot have multiple ages. The multi-valued attributes can have multiple values for the same attribute. For example, an employee can have a single or maybe multiple phone numbers. So the phone number attribute of the employee entity is a multi-valued attribute. The derived attributes are derivable from one or more other attributes. For example, the value of age attribute can be derived from the current date and the date of birth of an employee. So the age attribute is called a derived attribute, and the date of birth attribute is called a stored attribute. These derived attributes need not be stored in the database, and they can be obtained programmatically. This will save storage space, and it can ensure that the attribute value is up to date. It is a design choice to be taken in the design phase, whether to collect the age information and store, or dynamically generate it by using date of birth attribute. This design decision can be taken carefully by considering the aspects such as performance of the application, storage space, and whether to always have the latest value of the attribute. In some cases, a particular attribute may not have any applicable value, or we do not know the value for an entity. In such situations, a special value called null is used for those attributes, and they are called null-valued attributes. There are two different meanings for the symbol null. They are not applicable and unknown. The unknown category of null can be further classified into two cases: missing and not known. In the missing case, it is known that the attribute value exists but is missing. For example, an employee might have a phone but the number is missing. In the not known case, the value of the attribute is unknown. For example, if we don't know whether an employee has a phone or not. If we group composite attributes and multi-valued attributes together as an attribute, those are called complex attributes. Here we represent composite attributes between parentheses and multi-valued attributes between braces. For example, to represent an employee who has multiple residences and each residence has only one address, but each residence have multiple phone numbers. A complex attribute can be used. Here we can say that residence is a complex attribute. Phone is both composite and multi-valued attribute, and address is a composite attribute. In this lecture, we have discussed some basic terms in database design. Knowing the concepts like entity types, entity sets, keys, and value sets gives us a better understanding in designing and working with a database. So let's get started. An entity type is a collection of entities that have the same attributes. For example, all the employee entities will have the same set of attributes, and each attribute will have its own value or values. And this collection of employee entities is called an employee entity type. In the employee entity type, here are 3 entities, and each entity has a name, age, and salary attributes, and each attribute has a value. For example, the value of the name attribute of the first employee is John Smith. A collection of some or all entities of a particular entity type in the database at any point in time is called an entity set or entity collection. For example, employee refers to both an entity type as well as an entity set. Key attributes has one or more attributes whose values are distinct for each individual entity in the entity set. Its values can be used to identify an entity uniquely. For the employee entity type, a key attribute can be an employee ID. Sometimes, a combination of the attribute values together form a composite key. For example, if there is no employee ID, then name and date of birth can form a composite key together. If an attribute is associated with a set of values, then the set of values is called a value set for the attribute. For example, if the range of ages allowed for employees is in between 16 and 70, then the value set of the age attribute is a set of integer numbers between 16 and 70. The attribute manager of the department entity refers to an employee who manages the department. The attribute controlling department of the project entity refers to the department that controls the project. The attribute department of the employee entity refers to the department for which the employee works. Interestingly, all these statements are references, but not attributes. We represent these references as relationships. In the initial stages of design, relationships are captured in the form of attributes. As the design is refined, these attributes get converted into relationships between entity types. Relationship type and relationship sets are just like entity types and entity sets. For example, consider the relationship type works for between the 2 entity types employee and department. It associates each employee with the department for which the employee works. Each relationship instance associates one employee entity and one department entity. The employees E1 and E2 works for the department D1. The employee E3 works for the department D2, and the employee E4 works for the department D3. If we observe the works for relationship, there are 2 entities participating in the relationship, so the degree of this relationship is 2. The degree of a relationship type depends on the number of participating entity types. A relationship type of degree 2 is called binary, and of degree 3 is called ternary. Binary relationships are widely used relationships. In this video, we have discussed some basic concepts in the designing of database systems.
If a company has a rule that each employee must work for exactly one department, then, for such rules we need to define constraints. There are 2 types of binary relationship constraints: cardinality ratio and participation constraint. Cardinality ratio specifies the maximum number of relationship instances that an entity can participate in. For example, in the works for binary relationship type, department to employee is of cardinality ratio 1 to n. That is, each department can be related to any number of employees n, but an employee can work for at most one department. The possible cardinality ratios for the binary relationship types are 1 to 1, 1 to n to 1 and m to n. Participation constraint specifies an entity can exist only when it is related to another entity via a relationship type. It also specifies the minimum number of relationships that each entity can participate in. So it can also be called as the minimum cardinality constraint. There are two types of participation constraints: total and partial. If a company rule states that every employee must work for a department, then, the employee entity can exist only if it can participate in at least one works for relationship. So the employee E4 does not exist in the database. The participation of employee in works for relationship is a total participation. It is also called existence dependency. But every employee entity does not need to manage a department. So the employee E2 can exist in the database. An employee entity can exist without participating in the manages relationship. So the participation of employee in manages relationship is a partial participation. Structural constraint. If the cardinality ratio and participation constraint taken together, then it is structural constraint. For example, employee in works for relationship can be taken as a structural constraint because of two conditions. Condition 1 is an employee can work for at most one department, and Condition 2 is the employee entity can exist only if it participates in at least one works for relationship. There is one more interesting fact that relationship types also have attributes, just like entity types. For example, to record the number of hours per week that a particular employee works on a particular project, we can include an attribute hours for the works on relationship type. There are two kinds of entity types: strong entity types, weak entity types. Strong entity types have a key attribute. For example, employee, department, and project are strong entity types. The employee entity has a key attribute employee identification number. The department entity has key attributes name and number. The project entity has a key attributes name and number. Weak entity types do not have key attributes of their own. For example, dependent is a weak entity type in the dependence of relationship. A weak entity cannot be identified without an owner entity. An owner entity is an entity which is in relation with weak entity. Employee is the owner entity in the dependence of relationship. A weak entity type always has a total participation constraint or existence dependency. However, not every existence dependency results in a weak entity type. For example, department entity cannot exist unless it is related to an employee entity. But it has its own key department number. So it is not a weak entity. In this lecture, we have discussed about the constraints on binary relationship types. The data requirements of a company database are as follows. A company has several departments in it. Each department has a unique name, a unique number, and a manager for the department. A department can have several geographical locations. A department can control number of projects. Each project has a unique name, a unique number, and a single location. Each employee's database contains employees, identification code, name, address, salary, gender, and date of birth, etc. Furthermore, an employee should be assigned to only one department. But, the employee can work on several projects of different departments. Retrieve dependence information of each employee for insurance purposes, that is, including each dependent's first name, sex, date of birth, and relationship to the employee. Functional requirements of the client are: the client wanted to keep track of from how long a manager is managing the department and employees' working hours per week on each project. Initial conceptual design of the company database. Based on the discussion between designer and the client about data requirements. Designer can identify 4 entity types, and they are department, project, employee, dependent. The department entity type has department name, department number, locations, manager, and locations is the only multi-valued attribute. We can specify that both department name and department number as the key attributes because they were specified to be unique. The project has project name, project number, location, and controlling department attributes. Here, project name and project number are the key attributes. The employee entity type has employee name, employee identification, sex, address, salary, date of birth, department, and supervisor attributes. Employee name and address can be composite attributes. But, as it is not specified in the requirements, Database designer must check with the client again to verify if the employee name or address are composite or simple attributes. Assume that client have told designer employee name is a composite attribute, whereas address is a simple attribute. The dependent entity type has employee, dependent name, sex, date of birth, and relationship to the employee attributes. Based on the functional requirements, the database needs to keep track of the duration of the department manager. So, add an attribute manager start date to the manager entity type. Another requirement is that an employee can work on several projects, and also the database has to store the working hours per week of an employee on each project. So, add a multi-valued composite attribute worksin to the employee entity type. Project and hours are the simple attributes of the composite attribute worksin. In this episode we have discussed about a company's data and functional requirements and also the initial conceptual design of the company database. Now, let us refine the database design. Here, we convert the attributes that represent relationships into relationship types. From the requirements listed, we can determine the cardinality ratio and participation constraint of each relationship type. If we cannot determine the constraints, the users or clients must be questioned again. From the company database we have discussed, relationship types that can determine are manages, works for, controls, supervise, works on, dependence of. A manages is a one-to-one relationship type between employee and department. Participation of the employee is partial. Participation of department is total. A works for is a one-to-n or one-to-many relationship type between department and employee. Both the participations are total. Controls is a one-to-n relationship type between department and project. The participation of the project is total. The users indicate that some departments may control no projects. So, the participation of the department is partial. A supervise is a one-to-n relationship type between employee in the supervisor role and employee in the supervisee role. Database users indicate that not every employee is a supervisor and not every employee has a supervisor. So, both participations are partial. A workson is an m-to-n or many-to-many relationship type between employee and project. Both participations are total. Clients indicate that several employees can work on a single project. A dependence of is a one-to-n relationship type between employee and dependent. It is also the identifying relationship for the weak entity type dependent. The participation of the employee is partial. The participation of dependent is total. After specifying all the relationship types, we can remove attributes from the entity types. Manager and manager start date from department. Controlling department from project. Department, supervisor, and workson from employee. An employee from dependent. When we design the conceptual schema of a database, the data in the database should have the least possible redundancy. If some redundancy is required at the storage level or the user view level, it can be introduced later. In this lecture, we have discussed about refining the initial conceptual design of the company database. In this video we will discuss some of the additional features of ER model. The entities of an entity type E1, E2, E3 and E4 can be divided further into subgroupings or subtypes. For example, the members of the employee entity type can be distinguished further into engineer, secretary, manager, technician, salaried employee, hourly employee, and so on. Every entity that is a member of these subgroupings is also an employee. These subgroupings are called a subclass or subtype of the employee entity type. The employee entity type is called the superclass or supertype for each of these subclasses. A superclass-subclass relationship is a relationship between a superclass and any one of its subclasses. It is also called as a supertype-subtype, or class-subclass relationship. The relationship between a subclass and its superclass is called as is a subclass of relationship, or is a relationship. The member in a subclass is same as the member in the superclass but in a distinct specific role. For example, the entity Bill is an engineer and is also an employee. If an entity is a member of a subclass, it must also be a member of the superclass. However, it is not necessary that every entity in a superclass is a member of some subclass. Another important concept associated with subclasses is inheritance. An entity that is a member of a subclass inherits all the attributes of the entity as a member of the superclass. The entity also inherits all the relationships that the superclass participates in. Specialization is the process of defining subclasses for an entity type based on its characteristics of the entities. The entity type is called the superclass of the specialization. These concepts are displayed using enhanced ER diagrams. For example, the employee entity can be distinguished based on the job type as engineer, secretary and technician. This set of subclasses engineer, secretary, technician is a specialization of the superclass employee. We can have several specializations for the same entity type based on different distinguishing characteristics. For example, if we distinguish based on the method of pay, then we can define another specialization of the employee entity type as salaried employee, hourly employee. The enhanced entity relational diagram for the employee will be shown as follows. Attributes that belong solely to entities of a particular subclass. Like typing speed of secretary are attached to the rectangle representing that subclass. These are called specific or local attributes of the subclass. Here, D represents a disjoint constraint. It will be discussed in the next lectures. Generalization is the process of suppressing the differences among several entity types, identify their common features, and generalize them into a single superclass. It's a reverse process of specialization. For example, consider the entity types car and truck. The two will have several common attributes like vehicle number, price and license number. So, we can generalize them into an entity type vehicle. Both car and truck are now subclasses of the generalized superclass, vehicle. The enhanced ER diagram for the vehicle superclass will be shown as follows. In this video we have discussed about additional features, specialization, and generalization of ER model. There are two types of constraints. For example, in the employee entity type to determine the engineer subclass we can use a condition job type equals engineer. The entities of the employee whose attribute value for job type as engineer belong to the engineer subclass. If we use the same condition to determine the members of all the subclasses of specialization, then, the specialization is called as an attribute-defined specialization. The attribute is called the defining attribute of the specialization. For example, the job type attribute can be used to define other subclasses secretary and technician. In the enhanced ER diagram, a predicate-defined subclass will be displayed by writing the predicate condition next to the line that connects the subclass to the specialization circle. An attribute-defined specialization will be displayed by placing the defining attribute name next to the arc from the circle to the superclass. If there is no condition to determine members of a subclass, that subclass is called user-defined. Database users will determine the members in such a subclass. Two other types of constraints may apply to specialization are disjointness and completeness. Disjointness specifies that the subclasses of the specialization must be disjoint sets. That is, an entity can be a member of at most one of the subclasses of the specialization. For example, an employee can only be a member of any one of the subclasses secretary or engineer or technician. The attribute-defined specialization implies a disjointness constraint if the attribute used to define the condition is single-valued. For example, the attribute job type is a single-valued attribute because a job type attribute value can be any single value from secretary, engineer, technician, but not a set of values. So there is a disjointness constraint. The D in the circle denotes disjoint. If the subclasses are not disjoint, their entities will be overlapping. That is, the same entity may be a member of more than one subclass of the specialization. For example, a person can be a student at the same time he can also be an employee. Overlapping is displayed by placing a 0 in the circle. Completeness or totalness constraint has two types in it: a total specialization or a partial specialization. A total specialization constraint specifies that every entity in the superclass A, B and C must be a member of at least one subclass in the specialization. For example, if every employee must be a salaried employee or hourly employee, so this specialization is a total specialization of employee. In diagrams, total specialization is displayed by a double line connected to the superclass to the circle. If some entities of a superclass does not belong to any of the subclasses, then the specialization is called partial specialization. For example, not all employees belong to manager specialization, so it is called partial specialization. A single line is used to display the partial specialization. The disjointness and completeness constraints are independent. So, the possible constraints on a specialization are disjoint, total, disjoint, partial, overlapping total, overlapping partial. We can determine the right constraint based on the real-world condition. Because of these constraints, some rules will be applicable to specialization and generalization. If we delete an entity A from a superclass, it will automatically be deleted from all the subclasses to which it belongs. If we insert an entity A into a superclass, it will be inserted in all predicate-defined subclasses if the entity satisfies the condition. If we insert an entity in a superclass of a total specialization, it will also be inserted in at least one of its subclasses. If a subclass has further subclasses specified on it, then it forms a specialization hierarchy. The specialization hierarchy has a strict rule that every subclass must participate in only one class-subclass relationship, then each subclass has only one parent. So, this is called tree structure or strict hierarchy. For example, a person entity type forms a specialization hierarchy. In a specialization lattice, a subclass can participate in more than one class-subclass relationships. For example, a vehicle form a specialization lattice. A subclass can have many parent classes. These concepts apply equally to generalization. In the specialization process, the database designers start with an entity type and then define subclasses of the entity type. For example, to design a specialization lattice for a university database, initially we specify an entity type person. Then we discovered 3 types of persons in the database: employees, alumnus, and student. So we create the specialization as employees, alumnus, student. We choose overlapping constraint here because a person may belong to more than one of the subclasses. We can specialize employee into staff, faculty, student assistant. And student can be specialized into graduate, undergraduate. Finally, student assistant can be specialized into research assistant, teaching assistant. This process is called top-down conceptual refinement. If we follow the reverse procedure, then, that is called the generalization. For example, the database designers may first discover entity types such as staff, faculty, alumnus, graduate student, undergraduate student, research assistant, teaching assistant, and so on. Then, graduate, undergraduate can be generalized into student, research assistant, teaching assistant into student assistant, staff, faculty, student assistant into employee. Finally, employee, alumnus, student into person. This process is called a bottom-up conceptual synthesis. The final design resulting from both the methods might be identical. The only difference is the manner or the order in which they were created. Practically, the designers used the combination of the 2 processes. Conceptual database design is an iterative refinement process where the entities, relationships, and constraints are identified and displayed pictorially. Guidelines helps us to refine the design. Generally, many specializations and subclasses can be defined to make the conceptual model accurate. However, the design will become cluttered. We need to avoid this. If a subclass has few specific local attributes and no specific relationships, it can be merged into the superclass. The real-world rules drive the choice of constraints on specialization, generalization. That is to choose disjoint or overlapping and total or partial. If the requirements do not specify any particular constraints, the default would be overlapping and partial. Because this constraint does not specify any restrictions on subclass membership.